Bismillahirrahmanirrahim. Today I'm going to do my homework about communication system task 2. It says that we have to write a MATLAB code for AM, PM, FM modulation. So we will write the code and we will describe it step by step. So let's run to our code. I already wrote the code for saving the time to have the short video as possible. So let's start with first step. We have here clear close all clear CLC. It means it close all the previous operation and make the memory to start from zero. So at second we have our frequency parameters with 200 e times 3 with the frequency and time. We have time domain with 0.02 duration of signal, and here we have time vector, and this is our message frequency parameters with 200 the message tone 1 and with frequency of 200 hertz, frequency tone 2 with 800, and our amplitude with 1 and 0.6, and this is our message signal that we will send with all these down parameters. So let's start. This is our frequency of carrier, and this is our which is high, and this is our amplitude of our frequency. It's 1. So at the first figure we will make a figure that will show us our message signal. So let's start to see our message signal. It's as we can see here, this is our information or signal or message signal. We will operate this with all other parameters. So if we change the amplitude of our information signal from here, we could have to make it 3. Let's see what changes do we will have here. As you can see, the amplitude is up to 3. So this is how we can see. So now the amplitude for the first we had 1.0. So let's remain at that, because over amplitude will make the signal hard to transfer and PM or FM or AM modulation. So let's start here with the figure 1. So now after we will have we will start with our AM family. So at the first we have our modulation index. This modulation index is equal to 0.8 as far as we know. In AM modulation, in AM family, we have to have our modulation index between 0 and 1. If we make this modulation index 2, we will have overmodulated signal. So let's see what's the meaning of overmodulated signal. At the figure 2, we can see here our signal is overmodulated. If you want to make it clear, here we can see it's single sideband. We will see overmodulated down here. If we make this again 0.8, then we will see here no overmodulating, not overmodulating signal here, as we can see in the figure 3 here. And now we can see our single sideband signal is fine and it's going on its way, and the double side signal also the same as it was. So let's close these tabs, and we will see after that we will have second our double sideband from here. From here we will have our double sideband using hybrid transform SSB or upper sideband. So this is the code for it. So double side simply multiply message by carrier, no carrier component. So as far as we know, for double sideband with suppress carrier, simply multiply message by carrier. So we are here multiplying message with the carrier, so we will have our double sideband with suppress carrier. So at 3 here we have single sideband using hybrid transform. And we are here analyzing signal of message via hybrid transformation. So and here, as you can see, we have we have two sidebands in our the double sideband bits of risk carrier. What are those sidebands? One is upper sideband, and one of them is lower sideband. So if we want to find which one is our upper sideband and which one is the lower sideband, we can see here it is our upper sideband and this is our lower sideband. From there we can go to our fourth task. It starts from here. It said involve detector for AM simple reflector RC low pass. So now we are making demodulation here for after low pass. So involve the detector amplified to the conversion AM. So here this operation, it means for full wave reflector absolute value, simplify RC low pass smoothing uh, expectation. So we here we have our demodulation of RC time consumed distract distract second resolution for 2 kilohertz, and this is all how it's go. And here we have a four code, and we end as we know. So let's come further. So at here we have uh, coherent detector for AM and double sideband with fresh carrier multiply and low pass. So here coherent detector we are have code for coherent detector, as for the teacher give us the tags for AM family last. So here we have all our things written here. So after that we will start with the FM family. At first we will run our AM family, what we can see and what is available. So here, as we see our information signal available right here with amplitude of 1.5. Here we have our AM family. Here is our information signal, and here we have our modulated signal with every part is available. As we can see, every picture, every figure have its own meaning. So let's start. What is the first or the second or the third picture showing us? So here we have message signal. Here we have the corner AM signal, and here we have a upper sideband zoom, and here we have detector demand. We have single sideband signal here. As you can see, product before Laplace transformation of AM. This is after Laplace. It's our recovered signal after our recovered AM signal after Laplace. And here we have recovered double side Stokes-Fresquet after Laplace cornered with the amplitude of 1, and so we have our frequency like that here. So let's start with our second family, which is FM family. So at first we have frequency sensitivity radian per second per unit, because as far as we know, this is angular modulation. We at AM it was simple. We just multiplied carrier signal with the information signal, and then we got modulated signal. Here we have angular signal. We put this information signal uh, um, inside the carrier signal. So here we have our frequency sensitivity, and here we have max frequency derivation, and here we have uh, our this frequency at we showing it at hertz with an amplitude. And then at here our task started. This was the parameter. At first we narrowband FM small derivation approximation. So at first we have to make code for the narrowband. At first we have here we will directly generate small beta FM using pass modulation with small beta. as we know. So let's start with the this code. What's the code meaning of here? It is this boss of narrowband approx pass with the small beta. With small beta, this is our narrowband. So then we will have our wideband, and we will show it the pass, and this is our wideband signal here. And then we have FM with with signal with the direct integration method, but present as a direct integration. This is the same algorithm we show in the separately as required. This is the same algorithm, and we'll show it, and then we show it differently after. So here we have FM demodulator with the different with the here we can see our demod here we can see our the recovered dimension time is. So we will do our demodulation of the FM frequency here. So let me see, where was it? I hope I'm not lost. With demodulation fsdip. Here we are demodulating our frequency, FM frequency here, and then we have removing the carrier from here. We can see, and then here for after removing the carrier, we can see we will have low pass uh, control and system. From control system we can see we will put low pass, and then we will have our information signal. And then at here we have starting with the from here we are starting with our PM family. At first we have our narrow band, our narrow as far as we know, the PM and FM families are the same. We have just taken the derivatives, and then it will give us the FM family. So here we have our narrowband FM pass derivation, and then we will have wideband of the PM modulation, and then we have PM with direct pass here. So now we are want to print our figures. These are the code for the printing the figures, all the figures. So let's start for understanding our message, our figures. First we have our message signal with the parameter here. We, as I told you, so this is the amplitude. Let's change this frequency, make it our it to 1500, and then let's run our code. We will see that changing in our information signal, the frequency is so high. So for information signal, we have to have after we have the very high information signal frequency, we must make carrier frequency more higher. So at if the carrier if the message frequency is less, then our we can see our modulation will be more easier than before. So here we have our amplitude, and then let's start with the with the AM double sideband with refresh carrier informations. So these are with the figure second, as we can see, these are the plots. So let's make some changes in the signal, and we will see the big changes in the figures. So let's start at first, as I did before also. This is the modulation index. Modulation index must be between 1 and 8, and 1 and 0, between 0 and 1. So it we take it at a 0.8, as we see here. And then we will have double sideband and this fixed formula here, as we can see, cosine pi, the frequency of the carrier, as we have seen here, frequency of the carrier times t is here also available, and then double sideband we have our amplitude, and we have times cosine of the carrier. This is the carrier signal, and then these are all the parameters, and that's how it works. Thank you for listening.